Hello everyone, and welcome to Tagital, the show where we look at Tagital's source code and try to understand how to write a database which is distributed, which is reliable, which doesn't assume that the disk works, which can run on absolute garbage of the hard drive, which is implemented in Zig and which doesn't allocate memory. So let's get started. Last time was the first episode where we started to look at the storage layer of Tagital. So if you recall the overall architecture of our series, originally we discussed high-level decisions about Tagital, like why financial accounting, why no data definition language, why distributed, why consensus, blah, 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 blah. Then we zoomed into consensus and discussed how that works, at least most parts. One thing we haven't discussed yet is the state sync. And this is something which we'll be discussing after we discuss storage layer, because, well, state sync is about syncing storage. And to understand what work do you need to do to sync the storage, you need to understand what the storage even is. So today, last week, today, and for several weeks more, we'll be discussing this storage. How Tagital takes data of the network and writes it to disk, in which specific format where each byte goes. We won't be discussing how Tagital stores financial accounts in particular. So right now we're thinking about just, a sorted array of values. That's what we are going to store on disk, sorted array of things. How that maps to an account is going to be a topic of some of our future episodes. Okay, so the very last time we were discussing tables. So the basic kind of like unit of stuff that Tagital uses is a table. So again, our high-level task is to store a sorted array of values. A table is a subarray of a sorted array of values which we will be eventually storing. So kind of like a single building block, a table. So what's a table? A table is a bunch of blocks on disk. So for the purposes of storing data, we slice our data file into equally sized blocks. Each block is half a megabyte, if I'm not mistaken. Then we kind of like arrange all the data into those blocks. So a table is a sorted array of values logically, and physically it is a collection of blocks. Namely, it is one and only one index block, which contains pointers to value blocks and a bunch of value blocks. A value blocks is just a single array of sorted values stored on disk contiguously. And the index block refers to a value block using its checksum and its address on disk. I guess two important things to mention here. Addresses on disks are always U64, and in general, no matter what is your architecture, like 32-bit, 16-bit, 64-bit, you generally want to use U64 to address data on disk. So for example, when you do a SIG syscall on a 32-bit operating system, the offset is still going to be 64 bits because, well, disks might be larger than your memory. So here, this address is still like logical address of a block. So it is not a physical address of the first byte of the block on disk. It's just like it's the first block, the second block, the third block, etc., etc. So the physical address will get by multiplying this index by the size of the block, which is half a megabyte. But still, we use like U64 here. The second important bit here is that the checksum for value block is stored in the index block. So when we are going to read data block from disk, we already know its checksum. Again, this is something which mirrors the situation we had with our write-ahead journal. If you remember, the API to read a prepare from the journal, well, you don't need to remember, just look it up. Read prepare. Yeah, the API to read a prepare from the journal takes the checksum of a prepare as an argument. So this is kind of like one major invariant. Whenever you read anything from disk, you already should know its checksum, because it would be incorrect to store the checksum inside block itself. Why is that? Well, because disks have this very nasty failure mode, which is called misdirected reads or writes. When disk writes your data, not only can it corrupt the data, what it might actually do is that it could write correct data, but just to the wrong place. So you say, suppose you store the checksum inside your data block, and you say to your disk, okay, dear disk, please store this data over here. And disk says, okay, I got a request to store this data over here. I'm going to store this data over there. And then when you read this block, when you read that other block later, you're actually going to get wrong data. But because the checksum is in this block, well, you would consider this data to be valid, because like the internal checksum matches. It's just that the data it's not the data that you are looking for, to quote Star Wars. Okay, so yeah, we store checksums for the data blocks inside the index block. So that when we read the data block, we already know its checksum and can say that either the block is invalid, or maybe it was a valid block but just written at an erroneous offset. Of course, like the question arises, who stores the checksum of the index block? And well, the answer for that is going to be the manifest log block. And then the question is, well, who stores the checksum for the manifest log block? Well, that is going to be stored in the superblock. And for the superblock, well, I'll leave it as a cliffhanger, because obviously, like, this infinite regress of checksums stored elsewhere needs to stop somewhere. And well, this is an exercise for the reader to think where you and how you want to stop this infinite regress from happening. Okay, so we were we kind of like, one important thing, like, okay, so this is like a table is a bunch of blocks, one of which is an index block, and others are value blocks. value blocks store sorted array of values. So how do we actually find a value in a single table? Well, the answer is binary search. We have this very how do you call it? Elaborately named file called binary search, which implements binary search, and this value. Okay, it's not a real comment, likely. Yeah, and this binary search is used twice when we look up a value in a table. First of all, we binary search the index block to find the correct values block which might store our value. Because in the index block, not only we store checksums and addresses, we also store the minimum and maximum key of the corresponding data block. So by binary searching the index block, we can locate the desirable data block. And then, well, of course, we just binary search inside the data block to find a particular value. Okay, so that was table. There are like two problems with table. Why we can't store our entire data as a table. The first problem is that tables are just small. The index table is 0.5 MB, so you may stuff only so many references to values tables there. So the space of table is limited. The second problem with table is that table is immutable. If you have a table on disk, that you cannot just go into the middle of a table and change something over there, because you cannot you could theoretically read the table from disk, modify it in place and write it over, but it is first of all it's going to be horribly slow. And the second, it's actually not going to be reliable because if you will write an data in place and you crash in the middle of the process, then, well, you cannot recover. We need to have some extra data structure on top of our basic table to actually give us that mutable sorted array of values. And that structure is a tree. So I'm wondering what we should do here. Should we look first at the code which computes that limit about the table, which I alluded to, or whether we should look at the code for table. So, okay, so we'll cover a table a little bit later, but first of all, let's actually look explicitly at the code which computes the limit of number of values in a table. So if we understand, in theory, while tables are limited, because there is only a single index block, it's not too large, so you can have only so many values in there. But as usual with tagital, we have very precise knowledge about those limits. So let's look at the code which computes them. Again, this is, I think this should be in the table type code, and should be, okay. So probably the thing we are most interested at is value count max. How many individual values can be stored in the table? And okay, so this is actually passed in by the caller, and I think here we should try to validate this. So okay, if we create a table which stores at most table value count max values, then it needs at most this amount of data blocks, and the value, the maximum number of values inside a single block is the size of the block body, which is the size of the block minus the size of the header, divided by the size of the value. Okay, we should be ascertain this somewhere that we actually can properly store this in the index block, I think. Do we do this? Okay, yeah. We have this size of the index block, and it should be equal to the maximum number of data blocks multiplied by k-min, k-max plus address plus checksums. Okay, and how do we calculate this index size? So index is table index, and here we get size as, yeah. Here we just compute that size, and we assert that the size indeed fits in the block. So if you try to create a table passing too many values here, you'll get a compile time error which says, hey, actually, like you said that like your table needs to store like 10 billion values, but you know, to store 10 billion values, you need like 10,000 data blocks. And to store 10,000 data blocks, you need like 1.5 megabytes of the index block, but your index block is only half of a megabyte. So sorry, you need to store less values there. Okay, so basically the TLDR here is that it is on the caller to specify the maximum number of values that a table is allowed to store, and then table just asserts that, hey, I actually do have enough space to store exactly that amount of values. Okay, we'll get how that limit is computed when we get to modeling the actual data, I think. But for now, let's look at the tree. So, what is a tree? A tree aggregates a collection of tables to provide this single mutable sorted array of values. Okay, so how do we actually... Oh dear, what happened here? I wanted to move a browser tab to a new window. I didn't want to paste it into... I cannot use browsers. Okay. Okay, this is still our consensus stuff. Okay, so tree. What's a tree? Okay, this is a tree. I'm very bad at drawing trees, but for us, the idea behind the tree is that we take a bunch of tables. So let's think about like, okay, so we like understood the table is internally a bunch of blocks, but let's like abstract it away and think about table as just a sorted array of values. So table, a tree takes a bunch of individual tables and somehow arranges them to provide an illusion of a single array of a single mutable array of sorted values. So how can we go about doing that? Well, one case is easy. So let's say that we have two blocks. And it's true that all the values in the left block are smaller than all the values in the right block. So we can just take, well, not blocks, two tables, and all the values from the left table are smaller than the values from the right table. Then we can just arrange the blocks from left to right and say, okay, here is how like your view of a sorted array is this union of blocks. And you can actually go and arrange a whole layer of those things. Yeah, I meant to copy that. Okay. No. I want smaller. Let me kill that. Okay. So okay, there is like nice layer where blocks are sorted, tables are sorted, and values inside the individual table are also sorted. So you can binary search this thing. The question happens: what if you have two blocks that intersect? Oh dear, I can actually draw rectangles not by hand. You wish I knew that before. Okay, so let's say that, okay, that's too big of a block. Okay, let's say that you have this block and it actually intersects with both of these blocks. Well, what you can do here? Well, you can arrange a second layer of blocks. You can say, okay, this is the first layer, and this is the second layer. Tables in the first layer are disjoint, and tables in the second layer are also disjoint. However, between the layers, there might be intersections. But we say that the first layer has priority over the second one. So when we do a lookup, we first look up in this layer, and if we find our value, then we are done. If we don't find our value, then we go and look into the second layer. And if we found a value there, then we are done. And if we didn't find the value in both layers, we say that the value isn't there. Why this is a useful thing to have? Well, because this arrangement gives you mutability. So, okay, let's say that's like your current state of your sorted array. And you want to do a bunch of insertions into this tree. So, what you could do is that you can say, okay, so let's group a bunch of insertions into a new data block. And let's put this data block on top of our existing layer structure. And that way you kind of like non-destructively update things. So if your operation is actually overriding a particular value, okay, so I think I realized that I need to make something more explicit. So I say that we store sorted list of values, but important thing to keep in mind is that if this is the entire value, only part of the value is the actual key which we are sorting on. So the order of values is not total. The two values might be ordered equally, but they might actually be distinct. And that's how we actually are going to represent maps. So a map is going to be a set which stores a value where like the first part is the key and the second part is the value. So we compare these key value pairs only on the key. But like internally inside the code of our LSM tree, we still think of this as just a value. Okay, so that was a digression about values. Where was it? Okay, so yeah, we have a bunch of, we want to do a bunch of insertions. So we accumulate them into a new table. And then we just put this table on top. Okay, and that means because we look for a value from top to bottom, that means that if this contains an update, then this update actually shadows any previous values which compare equal to the new value. So when we do a lookup, if we hit something there, we actually don't look here. So let's actually, let's play this pictorially. Let's say that we have a value where comparable part says A, and incomparable part says 92, my favorite number. Okay, and let's say that this value was stored in this block. Okay, value is larger than the block, which is unfortunate, and I cannot make it significantly smaller, but okay, that's close enough. And then in this new update, we actually store a value which with the same key part A, but with a different value part, like 62, which is not to Julio Cortázar. Okay, the thing is, when we do lookup here, we will do lookup here for key A, we'll stop right at this block, and we won't look into the deeper layers because this is shadow. So this is like how you can take these immutable tables and make a mutable array out of it, which is essentially says, okay, so to modify the table, you don't have an operation to modify a single key value. You need to batch your updates. But if you have a whole table of updates, well, you just slap it as an extra layer. And like that works. So you could imagine that like this stack of layers like grows and grows and grows and grows, which works but isn't any more performant, because the thing is, while we have this arrangement inside the layer where the blocks are sorted, we can binary search within, I continue to say blocks, but of course I mean tables. You can binary search the tables, and then you can binary search inside the table. So within a single layer, our lookups are pretty fast. However, across layers, you essentially get a linked list. If you're looking up a value, you don't know whether it is here or here or here or here or here or here. So in each layer, you need to do a lookup, a linear lookup, and that scales linearly with the number of levels. And like what's more, again, in tagital, we want everything to be bounded, and with this like infinite stacking, you actually can get like arbitrary many levels until you get to the moon, like in that fairy tale about the bean which sprouted and grow like an enormous stalk. Okay, so what do we do here? Well, if stacking too many layers is too much work for us, then the answer is, okay, let's not stack too many layers. Okay, what will we do then? Okay, so let's say that this is the picture we have right now. So some layers exist in a new table, which was added on the previous iteration, and we want to insert a new table. What are we going to do? Well, the idea is to merge this table into the first layer. So let's say that this table intersects only with these two tables. So it doesn't intersect here, it doesn't intersect here, but here we have an intersection. So what we can do is that we can take these three tables, read their values, and produce a different three tables which are actually disjoint. So you see, here we have intersection, because I don't know. Okay, let's say that this is like the key A, B. Let's say that this is the key D. And this table stores keys from A to F. And okay, we need more than two keys. Okay, let's say we have like D and like some letter which is far in the end of the alphabet. I don't know. Let's say we have letter X. And this over here stores A, B, C, D, E, F, okay, G to Z. So you see, here we have like key with D and it intersects with this table. And here we have key with X and it intersects with this table. So this one here intersects with both of those tables. We can go read all those three tables in memory and reshuffle the keys into three disjoint tables. So that, I don't know, let's say that this gets over here, and this gets over here, and this one, keys from this table, get split between these two evenly, and same here, this one gets split between those two evenly. So okay, kind of like just, your typical merge sort kind of thing. And then you can insert that thing back into the original layer you had. So you have this, compaction operation. If you have two layers which are not disjoint, you can take a table from one layer and move it to the next layer, potentially overriding some tables. And that trick allows you to keep the number of layers and the number of tables in the layer constant. So without looking at much code, that was LSM3 for you, log structured merge tree. And that's exactly what this table structure in Zeek's source code manages. This stack of layers which with tables which move between the layers through compaction. And important that I say that compaction moves tables between the layer, but it isn't actually exactly what happens, because compaction actually overrides these tables. Compaction writes several tables from one layer, one table from the previous layer, and then reshuffles the union of values between different tables and writes the result as a new layer. Okay, so we won't be discussing compaction today because, we recently landed a giant refactor of our compaction. Not refactor, giant performance improvements, and that's fascinating to discuss, but that's too deep in the weeds. So right now we'll be looking just at the static picture and see how it works in the code. So we'll be thinking about an existing set of layers, and we won't be looking at how those layers get created. Okay, without further ado, let's dive right into the code. Okay, so tree. One thing I want to note is that we have this grid data structure, and grid data structure is central to all disk access, because grid is what ultimately manages this access to blocks. And I think we'll be looking at the implementation of the grid next time. But for now, assume that grid is just an abstraction which can read you arbitrary blocks from the disk. Okay, so what do we have in the tree? The main thing I'm interested in is lookup. And we actually have two lookup functions. We have lookup from I hate folding implementation in VS Code. It's so stupidly useless. Why cannot just fold me this function? Please fold this. If I select this, doesn't work. Okay, so yeah, sorry, no folding, no folding for. I'm just going to delete this. Yeah, but I will restore this code. Okay, so we have two lookup functions. One which lookups from cache, which means that it does lookup using only in-memory structures. And then the second one looks up from storage. And the one that looks up from storage is going to do a disk I/O, and that's why it is an asynchronous function. It accepts a callback. And that's actually an interesting pattern, because when you code asynchronous systems, it's important that either your operations are always synchronous or they are never synchronous. Because the caller should be able, when they pass a callback in, they should be able to assume whether they could get a Stack Overflow because the callback is invoked recursively or not. And one way to fake always synchronous API is for the synchronous case, just do how do you call this in JavaScript? Set timeout 0. So basically you say, okay, so invoke this callback on a pristine stack, but on the next iteration on the web. And we do have this API in tagital. But actually, most of the time, it's better to pass a button back to the user and let the user decide whether what we do with the synchronous and asynchronous part. So that's why we have two APIs here. The synchronous lookup from cache and the asynchronous lookup for storage. And the idea of the caller is that they synchronously call lookup from cache, and if they get a result, they deal with it immediately. Otherwise, well, they go and read stuff from disk. So let's look at the cached one, because that should be simpler. Thanks God, unfold works. Okay. Table immutable, table mutable. Do I want to talk about table mutable? Okay, so I don't want to talk about it, but I have to. Coming back to this beautiful picture, if you recall, the idea is that, well, you want to add a whole table of things at a time, because the data structure is simply incapable of operating on a single value at a time. Like it is inherently batched. And again, this idea of batching operations goes as a how do you call it in English? A red thread throughout the entire code of tagital. So it's batching all the way down. But the problem is, like, when you do individual operations with accounts, when you, like, subtract some amount of money, add some amount of money, like, those are individual operations. So you need like some sort of a cache which kind of like groups together those individual operations into a batch. So before you have a full-formed batch update to your table on disk, you need to have some in-memory thingy which does it. And that is sort of like table immutable stuff, which we'll get later. So, but for now, okay, let's ignore this. What I do want to talk about is this manifest thing. So what's manifest? Again, as I've said, like, we kind of arrange things in a collection of layers. The question is, well, who stores those layers? And the answer is the manifest. So the manifest is a thing which stores pointers to each specific table. Let's look how that works. Okay, manifest. As usual, generic type, generic over like table and storage. And what it stores is a bunch of levels, because our tree is organized in levels, and we have a manifest layer for each level. As we learned here, the number of layers is just constant, and it's a small constant. Like, we have like 7 layers. Yeah. Because, well, each layer is exponentially larger than the previous one. I think the factor is 16. So 7 layers is actually enough to store a whole lot of data. Okay, so what's inside a single level? That's a manifest level. And here we have a sorted segmented array, which is a data structure which I haven't looked at details before, so I might be slightly fuzzy here on details. Okay, and I think that's essentially also, what is it? What API does it have? Segmented array with an efficient okay, yeah, so it is basically a bunch of array lists arranged into a linked list. And I think it should have some sort of lookup function. Do we have lookup here, insert element? Remove. Do we have a lookup here? Interesting. I wonder if it really does. Oh, okay. Oh, here it is. Finally, at the line 885, we have a search function. So if we want to search for this segmented array for a key, I think what we do Oh, this is nifty. So this is a linked list of nodes, but the nodes themselves are arranged into the array. So again, this kind of like, this structure of nested binary searches repeats itself. So here we binary search the relevant node, and then we binary search within a single node. Okay, so I guess the bottom line here is that the sorted segmented array is a structure which supports relatively efficient binary searches and insertions. Actually, okay, so one thing I'm not sure about is that when we insert the node in the middle, we should be like, shifting those nodes. So I wonder if we do have a memcopy for nodes. Copy right. Copy disjoint. Oh dear, this is a lot of tricky. Oh, right. Yeah. So actually, when we insert a new node, we kind of like memory copy that whole array of nodes. But well, because this is sort of like like a B tree of 2 levels or some such. So kind of like we kind of like get I think SQRT complexity here. So we kind of like we do like those mem copies, but actually because the number of elements is like pretty slow, actually I think we could just compute how many. How many elements maximum we might have. Node capacity. Well, okay, like some complicated math, but anyway, the idea with that we kind of like don't copy the elements themselves, we copy only the nodes. And again, our elements are pointers to like the entire tables. So kind of like one mem copy here actually corresponds to like, dealing with like millions of underlying individual key value pairs. So this should be okay. So okay, probably one day we should like take a closer look at the segmented array. But for now, I want to discuss this manifesting. Okay, so we have level, and level stores a segmented array. Where was the segmented array? Oh well, it stores several segmented arrays. It stores a segmented array of keys, stores a segmented array of tables. Probably those are parallel. There's like this snapshot thing, which is not fully implemented, so we won't be covering it. And I think where is like search? Oh, we use it in binary search, so it should the place where we. Well, no, we're using it only for test. Well, because the actual binary search is hidden in the levels. Okay, well, maybe it's called lookup. Well, let's start with the manifest. Okay, so manifest stores a bunch of levels. Each level is internally sorted. So when we search something in the manifest, I think we should recursively. Okay, lookup. We should recursively look this. Okay, so this is this lookup function which takes a manifest and which returns a key and returns an iterator. While an iterator, well, manifest spans multiple levels, and our key kind of like might belong to multiple levels. So kind of like this, like for each level, it returns the table which might contain this thing. let's look how this iterator works. Okay, so we have a key, we have a current level, and the current level is presumably level 0 when we start this. Okay, and here we have the loop over levels. We do a quick check whether this level contains this key. And again, this is probably just, stored in some meter information. So yeah, we have like each level remembers the range of keys that are found in this level. So this is just a fast path check. Otherwise, we iterate through all the table in this level. Okay, yeah, so this explains why I wasn't finding the search. Because the level doesn't have search for individual key operation. Everything is batched, so it only has a search for this key range operation. But when we do an individual point lookup, well, we search for a range which contains only our single key. And again, we take the next table and we return this table if it hits. Okay. Yeah, and the important thing here is that a single level can contain only a single table which contains this key, because tables on levels are disjoint. So we actually assert that the next table is down here. And then we increment the level, so we return at most one table from each level. Okay, well, let's look how level iterator works. Okay, I'm amazed just how good Zig language servers go to definition actually works in this time heavy code. This is really great. Like, kudos to developers. Okay, so iterator. Okay, this is not a hard code, but it's just like, a lot of simple code stacked on top of like layer after layer. So it might be not super trivial to get this, because there is like stuff about visible and invisible tables, which refers to snapshots, which is not something we want to discuss right now. Well, we'll have to discuss that once we get to compaction. But okay, so we have, I guess the main thing is that we have a table iterator, and yeah, the table iterator we find by binary searching for specific key. And here we should have, well, how do we get the cursor here? Well, we already have it. Okay, target. Well, yeah, target is a cursor. Target is not just like, the key. And then we... Yeah, that's a binary search. So, okay. Digging ourselves from this stack of yaks, we are looking inside the manifest for a key. That means that we look for a key in each layer and then return iterator over layers. For looking inside a single layer, we don't have an API to do a point lookup. We only have an API to look up for a range of keys. So we binary search for a minimal key, and that's kind of like our start of the iterator. And then our iterator will be advanced. Yeah, and we'll so kind of like we binary search for the first table, and then we advance our iterator to the next table while the table still contains our key. And the important thing important thing is that important thing that everything in tagital actually stores the minimal range and the maximal range. So remember that the index table for each data blocks stores min and max. So before you get to the data blocks, you can actually say whether the data blocks might contain this thing. When a pointer to a table is stored in a manifest, this manifest stores min and max for the entire table. So you can quickly say if a key belongs to a particular table. And when multiple tables are arranged inside the level also stores a key min and key max. So you can quickly tell whether a value belongs to a particular level. So that's why kind of like, you could basically just binary search those things. There is a question in Twitch chat about which theme I'm using. I'm usually not answering statistic questions because that doesn't matter. Everyone uses whatever they're most comfortable with. But here actually would like to answer because this is the theme I kind of made. It's not really made. It's a port of Zenburn theme for Emacs because it's glorious theme, and it is also called Pale Fire because Pale Fire is just a perfect name for not in a block of Snowball, which is also good, but Pale Fire theme for VS Code. I kind of originally it's not true to say that I made it because I originally made it, but it's actually now maintained by a different person. You see, I'm not this the top contributor here. This Luna is really great at color themes, and she has a ton of different color themes, and I use a bunch of them. So thanks you for doing this awesome work. Anyway, color themes are important, but not main topic of today's discussion. Okay, so let's dig us up. So what we were looking at is the code in the manifest to find a table which might contain this key. So again, manifest contains only pointers to the table, so it cannot actually say whether the table has the key or not. For that you need to get actual table blocks, but it can say that if any table contains this key, that it must be this table. So we get this table in the manifest. When I say pointer to the table, in general, when we say pointer to anything on disk, we always mean a pair of an address and a checksum, because just address is not a pointer. If you assume that your storage might fail, you absolutely do need to have a checksum. Okay, so we have a table which is an address and checksum, and then we try to read, and this is address and the checksum of the index block. So we go and read from disk, and again, remember this is lookup from cache. So this is the code path for when we have all the data already in main memory. So this doesn't actually goes and read block from disk, rather it tries to read it from cache. If we don't have this block cached, we don't have the index block for this table in memory, we don't know whether the key might be in that table. So we return that, hey, this kind of this value might be in this table, but we gotta read from disk to get to it. The more interesting case is if this index block is there. Then we use this horribly called index blocks for key function, because it's not index blocks, because there is only single index block. Rather, using an index block, it looks up for the value blocks which might contain this key. And again, internally, table index block for key. Internally, this is again going to be just a binary search, because like everything is binary search in the storage layer. Okay, so blah 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 blah. If we don't have a corresponding block, then we move to the next table from the next level. If we moved all the way up to the bottom of the tree and we didn't find any block, any table which might contain this key, then we can confidently say without touching this that, hey, there isn't such key in our table. Otherwise, okay. Otherwise, we have like these blocks. Why key blocks? Why it is blocks? It should be called just like a key block. It's a single thing. It is a single thing, I hope. Index blocks for key. Yeah. Data block. Why? Okay, I don't understand this name. Perhaps before we had slightly different arrangement of data on disk, where you actually store like values and keys in separate blocks of disk. Whatever. Anyway, so the important point is that we have the address and the checksum of the data block, which might contain this key in this particular table. Then we, again, go and try to where it is. Okay, what is happening here? Am I looking for that code? Okay. I was scared that, like, we are calling this function here and I'm not finding it anywhere. And that actually is possible in Zig because, well, Zig compiles things lazily, and as long as you don't call this function, then it doesn't matter, then we are not calling it. And that will actually be horrible, because that means that we have a fast path for, looking up values from memory, and we don't ever call it, so Zig doesn't complain, and that means that we always do our lookup from disk, and that just, it's like multi orders of magnitude performance bug, but well, luckily I know where a function went. And remember when I was complaining that VS Code's folded implementation is absolutely unusable, I just say, okay, I'm going to delete the function. Well, that was exactly the function I was doing. Okay, so anyway, we find the address and the checksum of the data block. And then we, again, want to look up a value in this data block, but only if this value is present in the grid cache. So if this actual block is already in memory, because we don't want to go to disk here, because this is not an asynchronous function. Okay, this is, again, relatively straightforward. We ask the grid to get this block using, again, as always, pair of address and checksum. If we didn't get this block, we return block not in cache. And if block not in cache, we say, okay, we might have this value, but to do this, to know this for sure, we need to look it up from disk. And we actually, but we actually kind of, can say a positive amount of information. We can say, okay, this value cannot be found in any previous level. So that's why we, return value here. If the block is in cache, well, we look up value there, and if we didn't find the value, we say, okay, value isn't there, return negative. If the value is there, we return, the actual value, and then we return this all the way up to the core. which I think is it for today. So I guess in some sense this was kind of like the core episode about this LSM layer of tagital, because what we looked at today is the actual LSM. I guess the actual LSM would also include compaction code, but well, we kind of can with it. But yeah, that's like the basic structure of our data. So data is arranged in tables. Each table contains like a fixed number. Like each table has a bounded amount of values because it has only a single index block, and this block are limited in size, so you cannot store all the values inside a single table. That's why we arrange tables in layers, where each layer stores a set of disjoint tables. And then we have 7 layers stacked on top of each other. When we do lookups, we look up in a hierarchical fashion from the cache. So we kind of like, we look from all the layers from the first one to the 7th one, and the first layer where we get a value, we stop there. To do updates, which is something we haven't discussed yet, you kind of like first batch up an entire table of values, and then you merge it into the first layer, meaning that you take this table, you take all the tables that intersect with this table, and then you rewrite those tables to create a set of disjoint tables which can be put into a layer. When a layer overflows, we actually sync its tables further down to one layer below. And what we looked at today is how these lookup paths work. And that work is driven through the manifest data structure. So manifest is what stores a collection of layers. Well, I guess this thing is important to mention explicitly. Like, you know, when you like discuss how a database stores data on disk, it's important to keep in mind what data is stored in memory and what data is stored on disk. And important fact is that manifest, the entire manifest, is always in memory. So that means that in memory we store information about every single table that can exist on disk. And that means that the amplification factor between what we store in memory and what we store on hard drive is, well, the size of a single table. So because it's kind of like that's the crux of it. We are trying to optimize performance out of a memory hierarchy. We have small but fast RAM, and we have large but slow, relatively slow disk, crazily fast these days, relatively slow disk. And we kind of like want, like, obviously we cannot put all information from disk to RAM, because if we were able to do that, well, we wouldn't need a database. Well, actually it's a bit better. It's kind of like, well, even for a case where your data fits in RAM, you still want to use disk for persistence. And there is this interesting genre of a database which only use disk to provide durability across power failures, where all the actual data is stored securely in memory. But tagital is not that kind of database. We like assume that data might actually be larger than the total amount of available memory. But you need to store something in RAM. And what tagital stores in RAM is, first of all, the manifest. So it knows the entire set of tables that exist on disk. And it also this cache of blocks, which, you know, grows elastically with the amount of RAM you dedicate to your tagital instance. Okay, and manifest just like, you know, in-memory data structure with some more binary searches, linked list, and array lists. Probably we should look at segmented array one day, but not today. Okay, and we covered only the in-memory lookup path when lookup. Okay, table. Well, it's not a table, it's an attribute again. Tree is a collection of tables. Okay, lookup from cache. We looked at like the happy path where like all the relevant blocks are cached in memory, but it's useful for us to get a hand of how the data is logically structured. In a week at 5 p.m. UTC, live on Twitch on Thursday, we will be looking at the set path of this, where we need to go to this. And I'm not sure we actually go all the way up to lookup from level storage, but we certainly lay the groundwork because we are going to take a very close look at the grid and how read block from cache, read block from disk works. Okay, that's all for today, and thank you very much for joining. Hope to see you next week and answer all your Twitch questions. Okay, thanks and goodbye.